All right, so we want to talk about inequalities. And one inequality I want to talk about, let's just do less than first. So if I have two whole numbers, a and b, what does it mean that a is less than b? So you can't just say it's larger or anything like that, because I would ask the question, well, if b is larger than a, what does it mean for b to be larger? So see if you can carefully define this. Give it a go to try and define it. And the only things you're allowed to use are concepts that we've talked about before. So try and define it. And the things you're allowed to use, you can use, if you like, logic. So you can use ands and ors and quantifiers like there is or for all. You're allowed to use things like that. If you want to, you can use sets. And the other thing that we just talked about was the idea of addition. So you're allowed to use addition as well. So see if you can come up with a way of defining what it means for a to be less than b precisely, and the only things you're allowed to use are logic, sets, and addition. You don't have to use them all. You could use maybe 2 of the 3 and see if you can do that. It might be kind of hard to think this way, but it's a really good exercise to see if you can express concepts like this precisely. So pause the video now and really try this. Really think about it for a few minutes. See if you can come up with a good definition for what it means for a to be less than b. Okay, so this is kind of it's not a tricky concept. We all know what it means. But sometimes these things, these easy things, are very tricky to define accurately. Let's do a little number line here, just as an example to kind of get a feel for what's going on. Well, let's take, say, the number 3 and 7. Obviously, on the number line, 3 is less than 7. But how do we know that? Well, how do we know that using ideas like addition? We know that because we can add a number to 3 to get 7. We can add a whole number to get 7. We can add, of course, 4. And there's nothing special about 3 and 7. We don't even care that it's 4 that we're adding. But we know that, let's say, 1 is less than 7, because we can, of course, add 6. 5 is less than 7, because, of course, we can add 2. So the whole idea is that the smaller number is smaller than the bigger number. We can show that because we can add something. There is a number we can add to the smaller number to get the bigger number. So that's kind of the idea. So let's write it out. Definition. For a and b that are whole numbers, we say that a is less than b exactly when there is a, let's call it a c, some number c. And what kind of number do we want? Well, everything here is whole numbers, and we want to be able to add a whole number. So the smallest whole number we could add is 1. So c is going to be some sort of natural number or counting number. So there is a c that's a counting number, such that if I add c to a, I get b. So if a was 1 and b was 7, then the number that we add, our C, is 6. If A was 3 and B was 7, then the number that we add, our C, is 4. So if A is less than B, there's always going to be this natural number or counting number, C. Okay, so here's my next question for you guys. We defined less than. What about less than or equal to? How can we modify this definition to mean less than or equal to? So pause the video now and have a think about that. There's a few ways of doing it, but have a think about it. It might take a couple of minutes to come up with a good way, and then restart the video once you think you've found it. Okay, so there are two ways of doing it. One is a little bit clumsy, but it's not wrong. Let me tell you what it is. Well, we're talking about this meaning less than or equal to. So if A is less than B, then this is true, just what we wrote here. Or it can be equal, or we can say A equals B. So we can say exactly when, let's put an either here. Either there is a C such that A plus C equals B, or A equals B. So it's either less than, here's the less than part, or it's equal to. So that's one way of doing it. And I'm going to erase this because there's another kind of slicker way of doing it. And the slicker way is thinking about, well, if A and B were the same number, then what would I add to A to get B? If they were both, say, 7. If A was 7 and B was 7, 7 plus what gives you 7? And of course, the answer is 0. So if we want less than or equal to, another way of doing it is we just allow us to choose 0. Rather than taking our C from the counting numbers, 1, 2, 3, 4, 5, all the way to infinity, we take it from the whole numbers. Remember, if I put a little 0 here, this means that we're allowed 0 in the set as well. And in fact, I can just, as an aside, let me talk about a little note here. I can write the natural numbers, the whole numbers as the natural numbers, but union the set with 0. So that's another way of thinking of the whole numbers. So it's just the natural numbers, and then you union a set, or the set, with 0 in it. So there we go. We've defined what it means for A to be less than B, and for A to be less than or equal to B. And just a quick note here. We can define A is greater than or equal to B similarly. Because all you have to do is really, well, if A is greater than B, you can just say B is less than A. And we know how to do that from up here. And this is going to be important to us when we talk about subtraction, which we're going to do on the next slide. Before we talk about subtraction, I want to do one more little exemplar exercise with you guys, just to get some practice with some of these general proofs. So, imagine we have 3 whole numbers, A, B, and C, where A is less than B and B is less than C. I want you to show that if A is less than B and B is less than C, then A is less than C. And this is a very intuitive result. We know it's true. But how can we prove this algebraically? So my suggestion is to pause the video and try this yourself. The only way to get good at these kind of proof-style questions is to practice them and try them yourselves. Watching them isn't good enough, so I strongly suggest you pause the video and try it. Remember that back in section 1.4, I had a whole video on proving things, so go back, have a look at that, and just the steps will be kind of the same setup and everything. It'll just be that little middle part you'll have to figure out. So pause the video now and give this a try. Okay, so let's go ahead and try this. So remember, there are always two parts to a direct proof. We assume the if part is true, and we prove that the then part must be true. So let's assume the if part is true. So let's assume that A is less than B and B is less than C. All right, what does that mean? This means, well, we have a definition for what it means for A to be less than B. So let's use that definition. So this means there is let's call it, I don't know, we called it C in the definition on the previous slide, but we're using C as another number here, so we can't use C again. Let's pick something else. It doesn't really matter. Let's call it R, I guess. So there is some natural number, and I'm just going to name it R. We named it C in the definition, but it doesn't matter. You can call it whatever you like. So there is a number such that if I take A and I add R to it, I get B. Well, that means that A is less than B, and there is another number. Well, let's call it S, because B is less than C. We can do the same thing for B and C. There is some other natural number. It's a different natural number potentially, so I need a different variable name for it. I'm going to call it S, such that if I take B and I add S to it, I get C. So there we go. We've written down what it means for A to be less than B and B to be less than C. So we've wrote down our assumptions in nice forms we can use. It's usually a good idea if there's a way of translating it to some equation. Equations are very helpful for proving things, so it's a good idea to write it in an equation if you can, like what we did here. A is less than B is the same as A plus R equals B, etc. So we want to show that A is less than C, which means if A is less than C, that means I'll just kind of write this in shorthand, that A plus some natural number should give us C. That's what we want to show. And that bracket is going to be some natural number. Now we have to figure out how to show that. We know where we want to end up. So, if we know where we want to end up, we know we have these two equations. We have A plus R equals B. Maybe I'll actually underline these. And B plus S equals C. It would be nice if we could write these as A plus something equals C. So, looking at these two equations, It looks like in the second one on the right-hand side, I already have equals C. So I think this is going to help us quite a bit. But I have something in terms of B here and not A. If I can make this in terms of A, then I'll be done. But look at this equation up here. I have A plus R equals B. So I can do a substitution. Wherever I see this B, I can substitute A plus R since they equal. Since A plus R equals B, I can make that substitution. So I'm going to label these equations I and double I. And I can say, just so that the reader knows what I'm doing, substituting equation I into equation double I, we have that, well, B is the same as A plus R plus S equals C. So we're almost done. Now we just have to realize, hey, look, we can just change where the brackets are, and then this R plus S will be our natural number. So let's tell the reader we're doing that and why we can. So by associativity, we have that A plus R plus S equals C. And, well, we need that this is a natural number. And we can say, since R and S are natural numbers, remember up here, we said that they were. R is a natural number, S is a natural number. So, we know they're natural numbers. We know by closure that R plus S is also a natural number. So we're done. So the number we add to A to get C is R plus S. This is our natural number. So thus, A is indeed less than C. And again, I just want to point out what's going on. So the first part is literally just writing down what the if part means. That's what we did here. A is less than B, B is less than C. So we wrote out what that meant as an equation. The second part, well, we can always write this what we need to show. We're asked to show that A is less than C. And what does that mean? That means that A plus some natural number must equal C. So that's what we need to show. Now, all this bit here is where we have to be a little creative. In fact, really, the bulk of the creativity is just realizing that we can take these two equations, make that substitution to make it look like the way we want. But knowing how you want your answer to look is a good first step. Then you just have to puzzle through how to get that with the information that you have. You're always going to use your assumptions, so figure out how to combine those to get the result that you want. And for us, it was just substituting 1 into 2. B plus S equals C. Here's our B. B equals A plus R. So B plus S equals C. And then we just used associativity and closure to say that that the proof is done. All right. So I want to talk about subtraction just for a second. There's not too much to talk about here, since most of the setup we've already done when it comes to addition and inequalities. So let's talk about how to define subtraction only using stuff we've already defined. We've talked about what addition is. We've talked about what inequalities are. So we can do this. So let's take two whole numbers. Maybe I'll make this the whole numbers here, a and b. And we'll say that a is less than or equal to b. So that's going to be our condition. I put a little star here to say that once we get into other number systems other sets of numbers like the integers or the rational numbers, we won't need this because we're going to define subtraction a little bit differently, and we can relax what c can be a little bit. And in fact, what happens is we're going to kind of get rid of the operation of subtraction and turn it into an addition operation, so we won't even need to consider it. But for whole numbers, let's just say that a is the smaller of the two if there is indeed a small one. Then we're going to define what the subtraction b minus a is to be the unique number such that when you add that number to a, you get b. And let me just do a quick example all the way down here. So 11 minus 3, well, we know that's 8, since, well, I can take 3 and I add 8 to it, and I get, of course, 11. It's the only number that when I add to 3, I get 11. So that's how subtraction works, and we define it in terms of addition and inequalities. I don't want to spend too much time on the idea of models for subtraction. I will say there are at least 4 different models that the book talks about, something like the comparison model, and the takeaway model, and the missing addend model, and the number line model. So it's kind of useful reading those. So I suggest you look in chapter 2.3 and have a read of those models just to see how you can think about subtraction in terms of word problems. So it's a good section for sure. And the last thing I want to talk about with subtraction was the properties of it, or what's a better thing to say is the lack of properties. Subtraction is not a nice operation. Addition was very nice. It was closed, it was commutative, it was associative, everything was nice. But subtraction is not. Let's see. So, is it closed? Let's pick two numbers, 3 and 5. If I want to do 3 minus 5, well, 3 and 5 are whole numbers, of course, but 3 minus 5, we're kind of relaxing this condition here. But 3 minus 5 is negative 2. Negative 2 is not a whole number. Remember, this is just the numbers 0, 1, 2, 3, 4, all the way to infinity. There's no negative numbers on this set. So the whole numbers are not closed under subtraction. So we don't have closure. Is it commutative? Well, it's not. 2 minus 1 is 1. 1 minus 2 is negative 1. So you don't get the same answer. Order matters with subtraction. Grouping also matters. So 6 minus 4 minus 1, well, if we group the first two together, what do we get? Well, 6 minus 4 is 2. 2 minus 1 is, of course, 1. If we do it the other way, if we have 6 minus 4 minus 1, if we group the other way, well, we get 6 minus, well, 4 minus 1 is 3, and 6 minus 3 is, of course, 3. So you can see here that subtraction is not associative either. The different ways we put the brackets give us different answers. So it's not associative. The grouping matters as well. But it does have the property of 0. Any number minus 0 is itself. So at least we have that property.